Hello, I'm Patty Simpson with Simpson Math.
You can see that this is pretty much what we did last week, but it's going to tie into today's as well. It says you play a game where we roll a die 3 times. You win if you roll a 4, and you lose if you roll any other number. What is the probability of winning 2 out of 3 rolls? So as you're thinking about it, put it into words and comment while people are coming in. Go ahead and put it into words how you would find the probability. So think about using those conjunctions of and or, just like you did last week for that classical probability. Okay, so I like that exactly. So we have 4. So let me see if I can read them here. It says 4 and not 4. So that was a good warm up here from last time. If I'm rolling the dice 3 times, I'm going to have 3 entries. And I want to win 2 out of the 3 rolls. Well, that means 2 of my rolls need to be that 4. So Lily's got it here, 4 and not 4. Or, that was one of the ways. Another way to do it would be to say 4 and not 4 and 4. So 4 and not 4 and 4. Or that last way to do it would be 4, not 4 and 4 and 4. So not 4 and 4 and 4. So now let's put the probabilities with that. So what would be the probability that I would roll a 4 on a 6-sided die? You know, how many sides are there? That's going to be your denominator, and then the how many 4s are on the dice? That's going to be your numerator. So yeah, the probability that I roll this then would be 1 out of 6. The and tells me to multiply. The probability for getting a 4 here is 1 out of 6. The and tells me to multiply. And then how many not 4s are there? So what's the probability of not getting a 4, or of not a 4? Well, if the probability of getting a 4 is 1 out of 6, then the probability of not a 4 would be 5 out of 6. All right, now I'm going to add, and I've got 1/6 and 5/6 and 1/6. Notice that each time I roll that dice, every time I roll it, the probability that I roll a 4 on each roll is going to stay the same. It's going to be 1 out of 6. And the probability that I don't roll a 4 is going to be 5 out of 6. So here I've got 5 out of 6 and 1 out of 6 and 1 out of 6. So Eve wrote this down, this probability, but notice that there are 3 different ways. Good morning, Giselle. 3 different ways to do that. 1, 2, 3. So once we find this probability, we can just multiply it times 3. And we saw that last week when we were doing the classical probability, that once we found one of the probabilities, it was easy then. We just needed to know how many ways to do it. And in this case, there were 3 different ways to do it. So I could just take that 1/6. And the reason I'm doing 1/6 twice there, 1/6 times 1/6, is because I want 2 wins. I want 2 of those probabilities that I roll a 4. I need 2 of those. And then that failure, or that other thing, is going to be 5 out of 6. And you're exactly right. We're just going to take it and multiply it by 3, because once I have that probability, I know it's the same thing over and over again. I'm just multiplying it times 3. So I'm going to look for any reduction that I can as we go along. So for instance, here I have a 3 over a 1. Remember when I would multiply straight across, but I can do some simplification here, because 3 goes into 6 2 times. So instead of multiplying across and then figuring out how to reduce, now I look. The only thing I have on top is a 5. This is not going to simplify further, because 5 doesn't go into anything down here. So now I can multiply, and I've got 5 times, well, that's 36 doubled, or 72. So the probability, we find this probability of 2 wins and a loss, we find that once. But we know there are 3 different ways to do it, and so that 3 different ways, we just multiply it by 3. Now this leads in perfectly to the binomial distribution, which is what we're going to learn about today. In fact, you've already done it. You've been dealing with binomial distribution. You've just been with brute force figuring it out, because you would have to figure out all these different ways when we did the classical probability. In today's lecture, where we deal with binomial, the formula gives you the number of ways. In fact, remember back to the counting when we talked about combinations and permutations? This is really a combination problem. I'm looking at how many ways, remember those words? I was like, this is accounting when it says, how many ways can I get 2 wins out of 3? And y'all found that, but we could also use counting to help us to find out how many ways. Notice that here, where we rolled the 4s didn't matter. The order didn't matter. And so when we did order didn't matter, you remember what were we using when order didn't matter? This is a combination because order doesn't matter. And I'm going to show you how that's a combination. You know, I'm rolling it 3 times. So we have 3 things, and we are choosing 2 of them to be wins. So here, to find out the number of ways, we can do 3 choose 2. So you remember that combination and how order didn't matter? So when we're trying to find out how many different ways there are, we can use combination when because the order here doesn't matter. And we're rolling it 3 times, and we want 2 of those to be wins. I'm going to show you how that gives us this how many ways that we have. So let's go back and remind ourselves 3 choose 2. That formula, you put the 3 factorial on top. On bottom, you do 3 minus 2 factorial, and then the 2 factorial. And like Mr. Simpson said, we're going to learn later to do Pascal's triangle. Pascal's triangle is going to help us with these combinations. So here, 3 factorial. Well, I'm going to do the bottom first so that I have 1 factorial and 2 factorial. So I can stop at 2 as I count down. 3 times 2 factorial. Well, this 2 factorial and that 2 factorial become 1. This is just 1, so 3 divided by 1 is 3. Notice there were 3 different ways for us to get 2 wins. And sure enough, that's exactly what I have, is 3 different ways to get that. So the combination is going to tell us how many different ways. And then, because we wanted 2 wins, we used that probability twice, and then we had this failure of not a win, and we used that once. Now I'm going to show you the binomial formula and how all this fits in. The binomial distribution, the formula looks like this. The probability of some x is going to equal this combination. Now, by the way, we wrote combination as 3 choose 2. I can't remember now if I showed you this notation or not of 3 choose 2, but this means the same thing as that. Here we are doing a combination of 3 choose 2. Notice there's no vinculum here, there's no line there. It's just this notation without that line tells me I'm doing a combination. 3 choose 2. So I'm going to put some letters in here, some variables in here, but this is just going to tell us that we're going to have a combination to begin with that's going to tell us how many different ways we can have our number of wins. Then we're going to multiply that times the probability for success, or the probability for those wins, multiplied by itself that many times. So think about it here. We did the combination there. Then we took the 1/6 and we multiplied it by itself twice. So let me just show you in this one. Our x was 2 because we wanted 2 wins. Then we did this combination of 3 choose 2, the number of times we were rolling it, and how many wins we wanted. And then we multiplied it times that 1/6, that probability for success, the 1/6, we did that times itself 2 times because we wanted 2 wins. So we squared it because we wanted 2 wins. So here, this is what that says, is we're going to take our probability for success and just multiply it times itself, however many of those wins we want. And then this 5/6 is the probability for failure or not wins. Well, how many of those did we need? Well, since we were rolling it 3 times and 2 of them we wanted wins, well, there was 1 time that we didn't want to win. So we're going to use this Q to let us know that that's the complement of our P. And then to find this, we're going to do n minus x. So I feel like I jumped into the formula a little bit early, but you got the idea here with the formula where it's coming from. So now let me back up just a minute and tell you a little bit about a binomial distribution. In order for us to be able to use this formula, there are certain things that have to happen first. Number one, we have to have 2 outcomes. You see that binomial? So there are 2 possible outcomes. 2 possible outcomes. Or we can put them into groups that are 2 outcomes. So, we wanted a 4, and then there are a lot of different numbers on the dice, but we made it into 2 groups. We said 4s and not 4s. Those stayed the same, 4, not 4. Those were our 2 different groups. So you've got to have 2 possible outcomes. We're going to call one of them successes, and we're going to call the other ones failures. So we have our successes and our failures. You did that in your tasks when you split it up into black and white. You may have had a bunch of different colored M&Ms or starbursts, or maybe you had pens, markers, but you split it up into pens and markers, or pink and not pink, or whatever it was you were doing. You did that. So we are going to have, in order to have a binomial, you have to have 2 possible outcomes, a success and a failure. Then the second thing that has to happen is our probability must remain the same. So the probability must remain the same. Probability, let me switch hands. Probability must remain the same. So the probability for success has to stay the same each time. Think about when we roll that dice, it's always 1/6. Now think about your 2 tasks that you did. In one of them, the probability stayed the same every time. But in the other one, the probability didn't stay the same. Hey, Brandy. Hey, Bo. A bunch of y'all have added back. Hey, Adam. Tashara. Yay! We got lots of people joining. Way to go, guys. Way to be here in class. Okay, so here the probability must remain the same. And so in those 2 tasks you did last week, one of them the probability changed, and one of them the probability remained the same. So that probability that it remained the same was with replacement. Remember when you put it back in? So in this one you can kind of think of as with replacement, but not always, because like in this case with the dice, we're not replacing anything. Each one of those dice rolls is just independent, and every single time the dice, the roll of 4 is 1/6. It just stays the same on each one of them. So now, number 3, third thing that has to happen is we have to have a fixed number of trials. Fixed number of trials. And all I mean by that, when I say a fixed number of trials, I just mean that we're going to roll the dice a certain number of times. So I'm not just going to infinitely keep rolling the dice over and over again. We said we were going to roll the dice 3 times. Or when you were drawing from the marbles from the bin, you drew 3 marbles out of the urn. So there's going to be a fixed number of trials each time. Okay, so these are the conditions that have to be met in order for it to be a binomial. You have to have 2 outcomes. Each one of your things must be independent, and so therefore the probability must remain the same. Or you can kind of think with replacement. And then we have a fixed number of trials on each one of these. If we have that set up, then we can use a binomial distribution. We can use this formula. Now let me tell you about these letters that are in here. So what are these variables? Well, let me start with the n. The n is that number of trials, equals the number of trials. So think about over here, we were rolling it 3 times. So we rolled that dice 3 times. And my experiment was rolling the dice. I rolled it 3 times. So that n is just the number of trials. The x is the number of successes that we want. So that's the number of successes that we're trying to get. So here I wanted 2 wins. So that's the number of successes that I want. Then my p is the probability of that success, the probability of success, which remains the same every time. That's one of the conditions there. So the probability of success is my p, and then my q is the complement of p, or you could say 1 minus p to get that probability, or you could just say it's the probability of failure. Probability of failure. But if you're having trouble with coming up with what that probability is, it's just going to be 1 minus your probabilities for success. Notice we didn't do 1 minus 1/6 to get the 5/6. We just said, well, what's the probability that we don't roll a 4? And we knew that it was 5/6. But notice also that this 1/6 plus 5/6 gives me one whole thing. That's all of the outcomes that could possibly happen from rolling a die. So here is the binomial formula that we're going to use throughout this lecture today. And we're going to see that we did this without the formula. We figured it out without the formula. The formula just helps to move it along a little faster for us. Okay, let me give you some examples. It said, the first one we're going to do is, you are taking a multiple choice quiz that consists of 5 questions. So on the test, picture what's going on. So on the test, there are 5 questions on there. Each question has 4 possible answers, only one of which is correct. So, you know, each one of your questions has 4 answers. This guy is correct. Find the probability. To complete the quiz, you just randomly guess. You have no clue what any of the words on there are saying. You're just randomly guessing. Maybe you even roll a dice to help you figure out, a 4-sided dice to help you figure out which answer you're going to put on there. Or use a number generator or something to help you. You are truly randomly just guessing to the answers to each of the questions. And I want to know, what's the probability that you get exactly 3 answers correct? 3 out of 5 would be a 60%. That would be a D, be passing. So I just want to pass. I want to know, what's the probability I get exactly 3 correct? So first thing we want to do is just see, can we use the binomial? Does it have 2 outcomes? That's our first thing we have to figure out. So you tell me, do I have 2 outcomes to this question? Perfect. It's either wrong or correct. Those are your 2 outcomes. It's either going to be right or wrong. Those are your 2 outcomes. All right. So we have the 2 outcomes. Check. Next thing we need to know is the probability the same every single time? So what is the probability that I get a correct answer? So we know that there are 2 possible outcomes. Those two possible outcomes were right or wrong. Now, I want to know, is the probability the same? Is the probability the same each time? So what is the probability for getting a right answer? Perfect. It is 1 out of the 4 answers is correct. So the probability does stay the same for each one of the questions. And do we have a fixed number of trials? In other words, are there a fixed number of questions on my test? So that I'm not doing an infinite number of questions. Is there a fixed number of questions? And if so, how many of those, how many trials are there going to be? So we have 5 questions. So there are 5, so it's a fixed number of trials on there. It meets all our conditions, so therefore we can use this binomial formula. So now it's just a matter of figuring out my variables and plugging it into the formula. Now's the no fun stuff. This is just the tedious stuff, so let's do this. Our n, our number of trials, is 5. You've already told me that. That's our number of trials. Our x is, well, how many ones? Let's answer Mr. Simpson's questions first. So what is my q? If my probability for success is 1/4, what's that probability for failure? What's the probability that I get it wrong then? Good, 3/4. Perfect. Because there are 3 wrong answers out of every 4. And notice that 3/4 plus 1/4 makes the whole thing. They are complements of one another. Then, how many of these do I want to get right? How many successes do I need? Or how many successes do I want? So we go back and look, and I want to get exactly 3 answers correct. So my number of successes here is 3. Now it's just a matter of putting it into the formula, or even thinking through the formula. Man, y'all are doing great this morning. Y'all are on fire. All right, so thinking through the formula. What we want first is, how many different ways can I get it right? You know, I could get the first one right, and then get the second one right, get the third one right, and then wrong and wrong. Or I could get the first one right, the second one wrong. I don't have to go through all those possibilities. We know that we can find out the number of possibilities by just finding the combination. We have 5 trials, 5 different questions, and we want 3 of them to be right. So we have 5, choose 3. So that's where that combination comes into play. It's just telling us how many different ways there are that can be right. Then we're going to look at the probability for success. So we do our probability, that 1/4. You know, if I'm doing it's right and right and right and wrong, or, you know, there are this many, however many that combination is, different ways to do that. I'm going to find the probability for that right. Well, how many times am I going to put that down? 3 times, because that's how many successes I want. So I'm going to do 1/4 to the 3rd power, 1/4 times 1/4 times 1/4. Then I'm going to multiply that times the probability for failure. Well, y'all told me that was 3/4. The probability I get it wrong is 3/4. And how many of those wrongs do I need? Well, if I do 3 rights, that means that there are 2 left over that need to be wrong. Or we're going to square it. So you see how doing this classical probability that we did last time, this is just going to make it a little bit easier, because I'm not going to have to come up with all the ors. The combination is going to tell me how many different ways there are for me to do it. But I still do need to be able to think about, you know, what is the probability there that I'm coming up with each one, or the probability of my successes and my failures. All right, so here's what we're doing. We're finding the probability of exactly 3. Now I'm going to do some arithmetic. This is my combination. Notice I did not draw a vinculum. If you guys don't draw a vinculum on there, there's no line there. It's just 5, choose 3 here. On top I have 5 factorial. On bottom I have 5 minus 3 factorial. And then 3 factorial. Remember, that's that formula for the combination. Now this cubed means I'm doing 1/4 times 1/4 times 1/4 times 3/4 times 3/4. I'm going to keep going in a linear fashion. I know a lot of you guys like to take a piece of it and go off to the side and work off to the side. I don't know, it makes it really hard to stay organized that way. It might be better just to go in a nice linear fashion so that you can follow from step to step. So here, I'm going to keep going. This 5 factorial, well, on bottom I'm going to have 2 factorial and 3 factorial. So I'm going to stop at 3. 5 times 4 times 3 factorial. This 3 factorial and that 3 factorial become 1. This 2 factorial is 2 times 1. Well, notice that 2 times 1 is just equal to 2, and that goes into 4 2 times. So I'm going to go ahead and simplify there. So all I have left on that is 5 times 2. And I'm multiplying that times this 1/4 times 1/4 times 1/4, oops, 1/4, times 3/4 times 3/4. I'm going to keep it together, 1/4 times 1/4, and y'all are like, why don't you just multiply it out, Miss Simpson? I'm trying to get y'all where you will simplify first. So you're right, there are 10 different ways for us to come up with to do how we could get 3 right and 2 wrong. Now think about when we were having to do the classical, our lesson last week, to have to come up with all those 10 possibilities. Man, that'd be a lot, wouldn't it? So this just makes it a little bit easier for us to know there are 10 of them. Then I'm going to show you, I'm going to simplify here before I multiply. Again, this will help us not have to reduce later, and a lot of you missed out on reducing at various points in the assignments. So you want to make sure before you multiply, look for any reduction. Notice that these guys are up on top. So this 2 can go into that 4 2 times. So now 5 can't go into 4 or 2. And 3 can't go into 4 or 2, so I know that I can't reduce it any further. So now I just have on top 5 times 3, which is 15, times 3, which is 45. And on bottom, I have 4 times 4 times 4 times 4. That's 4 to the 4th power, which is 256. You know, this is 16 times 16, which gives me 256. Double that, and you've got 45 over, well, that's 12, carry 1, 10, 11, carry 1, 4, 5, 512. So the probability that I get exactly 3 right is 45 over 512. You know, if you wanted to find out about what percent that is, remember percent is out of 100. So we'd be dividing it by about 5, a little bit more than, 5. But we'll go with 5 because that will get us close. We can approximate that way. If you divide the bottom by 5 to get down to 100, then you divide the top by 5 to get down to 100, and it's about 9%. You can see we can approximate that. It's about 9% of the time we're going to get exactly 3 correct. We're going to make that 60 on there. All right, now I'm going to take this same question and I'm now going to look at least 1 correct. What if I want to get exactly 1 correct? So what changes on here? Well, first of all, what does it mean to be at least 1? So if I'm doing at least 1, then, if the doctor tells me to put at least 1 bandage on the patient, how many bandages am I going to put on there? So for just a second, I'm going to make this disappear. And let's just think about for a minute. how many different, in this problem, how many different outcomes are there? Like, how many could I get right? Let's think about our probability distribution. Think about your possible outcomes. If I've got 5 questions, how many could I get right? Well, I could get 0 right, or I could get 1 right, or I could get 2 right, or I could get 3 right. I'm going to stop somewhere on there. I'm going to stop at 5. Good. And you're right, at least 5, at least 1 correct means that I'm going to get 1 right, or 2 right, or 3 right, or 4 right, or 5 right. This is at least 1. So to find out the probability that I get at least 1 right, I'm going to do 1 or 2 or 3 or 4 or 5. In other words, I would have to do this formula 5 times, like this. I would have to say the probability, oops, maybe I didn't need to erase that. The probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 to get at least 1. That means I'm doing the formula 5 different times. Can you think of an easier way, maybe another way that we could do this instead of doing the probability of 1 plus the probability of 2 plus the probability of 3? When I start having to do that much work, I start thinking about the complement. So could we use the complement here? And if so, what is our complement? Yay, y'all got it. So, Bo, you're close, but at most one includes the 1. At most one is 1 or 0. You know, if my doctor tells me to put at most 1 bandage on there, I can put 1 on there, or I can put 0 on there. But notice that these two overlap. So they're not complements of one another because they overlap with one another. So look at this at least 1. What's missing from the group? Notice that just the 0 is missing. So the complement of at least 1 is just 0. Complement of at least 1. And notice that together they make up the whole set. So the complement of at least 1 is just 0. So instead of finding all this, let's just find the complement of it. If we add the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5, in other words, if I want to know how probable is it that I get 0, 1, 2, 3, 4, or 5 correct on the test, well, one of those things is going to happen. It's 100% sure that I'm going to have one of those things happen. So this whole set equals 1. So what I'm going to do is I'm going to find the probability of 0 and subtract it from that 1. And then that'll give me the probability of at least 1. So notice here I've got 1. If I subtract the probability of 0 from both sides, it gives me this probability. It's going to leave me with just that part. So that equals 1 minus the probability of 0. So to find the complement, I'm just going to take one whole thing, the whole set, and subtract that probability of 0. Maybe this helps us to visualize better that whole complement idea. So let's do that. Let's find the probability of 0 and then just subtract it from 1. So if I'm finding the probability of 0, well, my fixed number of trials is still 5. But the number of successes I'm looking for is now 0. The probability for that success stays the same. It's still 1 out of 4. And the probability for failure is still 3 out of 4. So the only thing that changed there was my number of successes that we're looking for. I'm going to erase this so I can do the formula now. So now we just plug it into the formula. We say the probability that I want 0 correct. Well, how many different ways can I get 0 correct? You know, if I'm doing the problems, well, you can kind of think about it. The only way I can get 0 correct is to get it wrong and wrong and wrong and wrong and wrong. All 5 of the questions have to be wrong in order for that to happen. So here I'm going to multiply that times my probability for success. How many times? 0 times. I'm not going to multiply times the probability for success. I didn't get any correct, which means I got 5 of them wrong. So I'm doing the probability, you know, think about it as wrong, 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 and wrong, and wrong, and wrong, and wrong. Well, I would multiply this times itself 5 times. So now, how many different ways are there? Well, 5 choose 0 is 5 factorial over 5 minus 0 factorial. 0 factorial. We're going to look at the Pascal's triangle tomorrow, and we'll get really fast at being able to do some of these combinations. Plus, just the more you do it, the faster you're going to get at it. Remember, anything raised to the 0 power, any of our probabilities here raised to the 0 power is just going to equal 1. Non-zero number raised to 0 power is 1. And then this is 3/4 times 3/4 times 3/4 times 3/4 times 3/4. Now, this is 1. So on top here I have 5 factorial. Remember, that's just equal to 1. On bottom here I have 5 factorial. So again, that's just equal to 1. So I just have 1. There was only one way for me to get them all wrong. I had to do wrong and wrong and wrong and wrong and wrong. There was only one way to do that this time. Times that 1 just gives me 1. So really all I'm left with is this 3 times 3 times 3 times 3 times 3. So 3 to the 5th power, well, that's 9 times 9 is 81, times 9 is 729, I think. Somebody can check my math there. And here I've got 16 times 16 is 256, times another 4, I think, is 1024. So the probability that I get 0 right is 729 over 1024. But I wanted to know the probability that I got at least 1. So that's this probability, you know, that's this probability of 729 over 1024. But now I wanted to know this probability, that I get at least 1 right. So what I'm going to do is take this and subtract it, because all these guys should add up to be 1. So I'm going to do the probability at least 1, so it's 1 or bigger. I do 1 minus that 729 over 1024. Remember, 1 is just this denominator over itself, because I have to have a common denominator. When I'm adding, I must have a common denominator. And then I subtract the 729 over 1024, and you guys tell me, wait, did I do that wrong? Oh. 9 times 9 is 81. Oh, it sure is. It's 243. Darn it. So this is 243. I don't know what I was multiplying. You're right. You're right. Just making sure you're with me. I was just making sure you're here with me in class. Way to be on top of things. Great job. So now I'm subtracting that 243. Good job. Good job. I don't know where I came up with 729. I was really just testing y'all. That's what that was. Now, I'm going to subtract. So this minus that 243 because I want the probability of the full set minus that. Let's fix it here too. This is wrong too. 243. So now do that subtraction and just tell me what it is so I don't have to. So 1,024, that's the part of the classroom environment I'm missing out on is y'all do the math and tell me so then I'm not doing it. That's 1, 12 is 8, make that a 9. So now maybe that's 781, see if it really is. Yay! Or maybe it's 8, wait, which one is it? Yeah, it's 7, I think it's 7. I think we got a bar there. Okay, so this is the probability that I get at least one right. Now, let's look and see. That last little bit with this question, I just want to know what's the probability that I get less than one correctly. Or less than one correct. What's the probability I get? These guys are weird. Answers, why didn't it just say correct? Less than one correct. Well, in order to get less than one correct, I only want to get 0 correct. That's less than 1. You know, anything less than 1 is 0. We already found that probability. It was 243 over 1,024. So notice that this is also just less than 1. 0 is the only thing less than 1. And that's the complement. Less than 1 is the complement to at least 1. Complicated. All right, so there's an example of using that binomial. So we don't have to go through that whole classical thing. Instead, we can just use this binomial if the conditions exist. So let's look at this next one and see if the conditions are met on this one. So a surgical technique is performed on 6 patients. You are told there's a, oops, I think it's an 80% chance of success. Find the probability that the surgery is successful for exactly 4 patients. So, in other words, you're going to go in and do a surgery, and you know that there's 80% chance that there's going to be success, and the doctor's performing 6 of those. He's going to do it on 6 patients. You want to know what's the probability that exactly 4 patients have a successful surgery. So let's think first, is this binomial? In other words, are there 2 outcomes? Yes, it does meet those conditions, the 2 conditions, because we have success or failure. Either it works or doesn't work. Then what about, is there a fixed probability? In other words, does the probability stay the same each time? Yes, it's an 80% chance for each person going in that their surgery is successful. And then the last thing, so there's 2 outcomes, the probability stays the same, and then the third thing, is there a fixed number of trials? That's kind of where I go to, Eve, is the life or death. And there are a fixed number of trials. He's not going to do this infinite number of times. He's got a fixed number. He's doing it with 6 patients. So our conditions for binomial are met. We have 2 possible outcomes, life or death. Maybe it's not always life and death. Maybe it's vision or not vision. You know, my dad just had eye surgery. Maybe it's to be able to see or not be able to see. Or maybe it's, to be able to walk or not be able to walk, whatever. But success or failure. The probability for success does stay the same. My probability each time is 80%. So I have that 80% probability. And there are a fixed number of trials. There are 6 patients that we're going to do this on. So there are a fixed number of trials. So now let's go through the formula. So you told me my n, which is my number of trials, is 6. You told me my probability for success was 80%. We could write that as 80%. You know, I could write that as 80%. Or maybe I write that as 80 over 100, which of course simplifies down to 4/5. Now, if my probability for success is 4/5, what's my probability for failure? Or what's the complement to that? What is my probability that I fail? The complement to that. Good, that's just 1/5. You could say 20%, because 80% plus 20% makes 100, but that, again, is just 20 over 100, which just reduces down to 1/5. Notice, 4/5 plus 1/5 makes the whole thing. Good job, guys. So that's my complement. Now I have to figure out my x. And my x is just the number of successes that I'm looking for. So in this case, I want to know the probability that I get 4 patients are successful. So my x value, my random variable here, is going to be 4. Just for a minute, let's look at the probability distribution, or look at the random variables, the possible outcomes. You know, if he's got 6 patients, he could have 0 success. He could have 1 successful patient. He could have 2 successful patients. He could have 3 successful patients, 4 successful patients, 5 successful patients, or 6 successful patients. So those are the different outcomes that he could have. 0, 1, 2, 3, 4, or 5 or 6. We're going to find the one for 4. For exactly 4 is what we're looking for. All right, so let me put the question back up here for you. So exactly 4. And Adam, you are exactly right. First thing we want to know is to find out how many different outcomes, you know, which ones of those patients are the ones that live and which ones die. So 6 choose 4, how many different ways could that happen? Then we're going to take this 4/5, that probability for success, and because 4 of our people are successful, we're multiplying that success times itself 4 times. Or you can think of this as to the 4th power. Then we take our probability for failure, and that means that some of the patients are not going to be successful. Well, if 4 of them are successful, then how many are not successful? Well, it's got to add up to be that 6. So what plus 4 is going to give me 6? That means that 2 of our patients are not going to be successful. So 4 are successful and 2 are failed. Now it's just a matter of doing the math. Again, I'm going to show you how we can do it nice and neatly on here. So that we have 6 factorial over 6 minus 4 factorial times 4 factorial. Then you've got 4/5 times 4/5 times 4/5 times 4/5 times 1/5 times 1/5. I'm going to do it in a nice, neat, linear fashion. So this is going to be 2. So I'm going to stop at 4 factorial on top. 6 times 5 times 4 factorial. This 4 factorial and that 4 factorial become 1. 2 times 1 is just 2. So 2 goes into 6 3 times. I have 4/5 times 4/5 times 4/5 times 4/5. This is what y'all don't want to do on your papers. You don't ever want to write it down over and over again, but I want you to. Feel free to do it. That way you won't make as many mistakes, and it'll help you to reduce later. Then here, notice there's a 5 on top and a 5 on bottom. So instead of multiplying all this out first and then having to reduce, I'm going to look for those reductions to begin with. And here I've got a 5 on top and a 5 on bottom that reduces. I mean, this is enough work multiplying without having to do it a little bit more. Now this 3 doesn't go into any of the 5s, the 4 doesn't go into any of the 5s, so now I can just multiply it out and know for sure that it's simplified. So here I have 16 times 16, which is 256. 256 times 3 is 3. You'll help me out with that. And then this is 5. This is 25 times 25, which is 625 times another 5, which is 3,125. So 3 times 256 was 18, carry 1. 15, 16, carry 1. 3 times 2 is 6, 768 maybe? Oh, I like it, 768. So we've got 768 over 3,125 is the probability there. Now, I want to know what's the probability of at least 4 patients. So let's go back and look again at this. We found the probability of 4 patients. But what about if I wanted the probability of at least 4 patients? So in other words, if I'm going to do at least 4 patients, which ones am I doing here? At least 4 means that I'm going to do a 4 or a 5 or a 6. So all of these are at least 4. Notice that doing the complement here is not going to be any easier, because the complement of 4, 5, 6, what is that complement of 4, 5, 6? What's the rest of the set to make that complement? Yeah, is 0, 1, 2, and 3. So this is the complement. I would actually be more work this time. So this is the complement of at least 4. So being able to write out your outcomes sometimes helps you to find that complement. And here's our early bird for the morning. We've got spin the spinner 100 times. How many times do you expect to win? You're right. If this is a fourth of my, this win is a fourth of my spinner. So I expect to win a fourth of the time. So I like that. Or you could even call a fourth 25%, right? So if I'm doing it 100 times and I expect to win 25% of the times, or a fourth of the times, I like that 25 times. So we expect to do, a fourth times 100, a fourth of the time, or 25 times. Or maybe you just said, well, that's 25% of 100, which again is 25 times. So we expect to win there 25 times. And this is, so let's think about what this means. That's what we expect to happen. It doesn't mean that it actually will happen. So for instance, yeah, that's exactly right. Our P here would be 25, or 1/4, and our Q then would be 3/4. So if I expect to win 25 times, how many times would I expect to lose then? Yeah, and notice that I'm not going to expect to win a fraction. I'm going to expect to win 25 times. Notice I'm getting out a whole number. Notice that how many times I get out a whole number. But when I ask what is the probability, then I get out a fraction. So if I asked you what's the probability, then you would give me that 25 over 100, or 1/4 would be the probability. Good, Aunt Carrie. Yeah, I would do 75 times. That's right. Good, Bo and Monty. Good. Y'all got this. So that's what I would expect to lose then 75 times. Now, it doesn't mean it will happen. That's my expectation. But, if I'm spinning it, I'm probably going to lose every single time. That's just how my luck works. It just happens that way. Whereas if Eve spins it, maybe she wins every time. Maybe she wins all 100 times. So in each one of us, if we go around and spin it 100 times, then what this 25 is on average, we should get 25. In other words, if Bo spins it 100 times, and maybe he wins 30 times, and Amani spins it, 100 times, maybe she wins 20 times, and Brandy spins it 100 times, and maybe she wins 25 times, and Kara spins it 100 times, and she wins 35 times. And Priscilla spins it 100 times, and she wins 25 times. I'm going to take all those winnings of 20 and 25 and 30 and 35, and I'm going to add them together and divide. I'm going to find the mean or the average of those. That average should turn out to be 25. That's what this expectation is we expect to win on average 25 times. So today we're going to talk about our expected value, our expectation, and that's all that is it's just an average. So let me put that down. Expected value. When I talk about the expected value, I'm really just talking about on average. And on this, I mean on the mean average. I'm talking about the mean. So on average, how many times do I get it? And I'm talking about the mean. Good. That's exactly what you're supposed to ask. So that's the expected value is on average, how many do I expect? And notice how we got that mean. By the way, I denote the expected value. You remember that mu symbol? The mu symbol was just the mean. Well, when I talk about my expected value, because it is just a mean, I use the mu symbol also to represent the expected value. And for binomials, finding this average is super easy. Notice what we did to find the average number of times we would spin it. All we did here was take the probability for success, the 1/4, you told me that was your P, your probability for success, and you multiplied it times your 100. Maybe I should back up and make sure that this is binomial. Is this actually binomial? Do I have two outcomes? Yeah, I've got a win and a lose. Those are two outcomes. Do I have a fixed number of trials? Yes, I'm spinning it 100 times. And does the probability remain the same every single time? Oh yeah, look, it stays 1/4 every single time, so it is binomial. And for this binomial, in order to find that average, or the expected amount, I just took the probability for success and multiplied it times the number of trials. So our expected value formula for binomial is nice and simple. Binomial expected value is just the number of trials times the probability of success. That's all it is. So let me change this for just a second. Instead of spinning the spinner of 100 times, let's do this. I want you to spin the spinner 48 times. What's the expected value of that experiment? Well, all I'm going to do is take my number of trials. So in this case, all I did was change that 100 to 48. And then I multiply it times my probability for success of 1/4, because success here is 1/4. And I end up with 12. So here I expect to get 12 wins. That's my expected value when I spin that spinner 48 times. Okay, now, do you remember standard deviation? Remember how we found standard deviation before? How we had that table? We put our x values, and then we had to find the distance from the mean, and then we had to find we had to square all those values, add them up and divide. Do you remember that complication? Hey, well, it turns out for binomial, it's so much easier. It's so much easier for standard deviation for the binomial. So if I want to find out how much this game varies, does it vary a lot? How much variability is there? What is the variance? What we do to find the variance of a binomial and remember the symbol for variance, that all we do is do the sigma squared. Remember, that's variance. This is variance. So now for the variance there, we're going to do, for binomial, it's just n times p times. So notice that's just the expected value. This is the same thing as that expected value. I could write it this way, or I could write it that way. Times q. So times the probability for failure. Try it, little sigma. It's exactly right. So what would the variance of this particular one be? If my variance is just the mean times that probability of failure. And Kara told us earlier what our Q was. She told us what our probability for failure was. So to find that variance, I'm just going to take and do this mean. So to find the variance, I'm just going to take my n times my p and then multiply that times my q, which Ann Kara told us was 3/4. So here, if I multiply that 12 times 3/4, put that 12 over 1, I'm going to go ahead and divide first so that I get 3 there. 4 goes into 12 3 times. Now I multiply straight across and I get 9. So the variance here is 9. Now, what is the standard deviation of it? Maybe you remember standard deviation, maybe not. But here it's a lot easier than it was before. But this is the same. Once I have the variance, how did I get the standard deviation? Remember, standard deviation was just that little sigma without the squared. So here's my standard deviation. And the way I get that is I just take my variance and take the square root of it. The square root of that variance. Or you could say the square root of the mean times your probability for failure. Or you could say the square root of n times p, because that's all mu is n times p times q. All these things mean the same thing. Once I do my n times my p, I have my mu, my expected value. And then once I have my expected value times my probability for failure, then I have my variance, take the square root of that, and I've got my standard deviation. So back over here, if I want to find the standard deviation of this, all I do is take the square root of 9, and I end up with 3. So the standard deviation is 3. My variance is 9, and my expected value, or the mean, is 12. Okay, now how in the world do we use all this? All right, let me erase this. I'm going to put these things over here just to help us remember. So today we're going to use this. We're going to use our mu, our expected value is n times p. Our variance is just that mu times q, and then our standard deviation is just going to be the square root of that variance. Okay, so I'm going to erase all this, and I'm going to show you how do we use this. Well, let's back up and remind ourselves about Chebyshevs. What do you remember about Chebyshev? Do you remember Chebyshevs? You remember that Chebyshevs tells me that for that 75% of my data is within 2 standard deviations of the mean? You remember that? And then what about 3 standard deviations from the mean? You remember what that was? I think it was 88.9%. Is that right? 88.9% is within 3. And remember, I'm forgetting 2 words on there that are super important, because it's at least 75% of the data, or at least 88.9% is within 3 standard deviations from the mean. Okay, so how do we use this? Well, I know my mean here is 12. I know my mean is 12. So if I go up 1 standard deviation, if I go up so on average, we're going to get 12. Correct. But 1 standard deviation is 15. Remember, you just add that 3 to both sides. And then add another 3 to it, and you get 18. So 2 standard deviations up is 18. Now I'm going to go back 2 standard deviations. So that I've got 11. That's not right. Subtract 3 from that. Subtract 3 from that. 9. 12 minus 3 is 9. I don't know how I came up with 11. And subtract 3 from that. I'm just going down that standard deviation, and I'm at 6. So this is 2 standard deviations below the mean. And 75% of the time, we should get between 6 and 18 spins. So, if I'm running a booth at a carnival, and I'm having kids come and spin the spinner 48 times, for some reason, then I would expect 75% of the time for them to win between 6 and 18 times. That would be the expectation for that to happen. Zoe, I'm counting up and down by 3 because my standard deviation is 3. So I'm adding 3 each time because this is up 1 standard deviation. Add another 3 and I've got 2 standard deviations. And the same thing back. If I go back 3, I'm going backwards a standard deviation. So it's just that distance from the mean. And I know at least 75% of the time I would get between 6 wins and 18 wins. So now go up 1 more standard deviation, 18, 19, 20, 21. And that's 3 standard deviations. Go back another one. I ran out of room. And I'm at 3. That's 3 standard deviations. So I know that at least 88.9% of the time that people are going to win between 3 and 21 times. Now, if something happens and I have 48 people come up one day to spin my spinner to win or lose, 88% of the time, let's say every day, 48 people come up and spin my spinner. Well, I know that I need to have that 88% of the time, I'm going to have 3 wins during the day, up to 21 wins. But let's say I start having, and it could happen on occasion, I could have something rare happen where I have more than that, because there's, this is just 88.9%. But let's say that over and over again, I start having people spinning more than 21 times, and it just happens over and over and over again. Then all of a sudden, I may be like, wait a minute, something's going on. My spinner's not working correctly, or these guys have figured out a way to spin it so that it lands funny every time. Maybe I got ringers in there that are cheating somehow. So I start looking at those different methods, start looking to see why do we have something weird going on. So I expect for 88.9% of the time there to be 3 to 21 wins. And if it's outside of that, and especially repeatedly, then I start thinking there's something weird going on. Let me check it out. So that's how we use Chebyshev's. That's how we use that standard deviation to help us out. So you can see, though, that today, finding our expected value and finding that standard variance and standard deviation isn't going to be too hard. A manufacturing plant produces defects 1% of the time. If the plant produces 1,100,000 parts a day, wow, they're really churning it out, man. Must be some easy part to spit out there. How many defects do we expect to produce? So if we've got 1,100,000, I feel like there's a, wait a minute. My commas are wrong. No wonder. Let's try that again. How about just 110,000? Oh, that makes more sense. Okay, good. 110,000. Numbers. Okay, 110,000. I like 110,000 better. So 110,000 parts a day. How many defects do we expect to produce? Still a lot. How many defects might we have? Okay, well, first of all, is this binomial? Can we just do that expectation? Well, it kind of makes sense just to multiply the number of trials times that 1%. If 1% of them are defects, I feel like we're just doing some multiplication there. 1% of 110,000. So let's just see if it really does fit that binomial. Are there 2 outcomes? Well, sure, it's defect or not a defect. And is the probability remain the same for them to be a defect? Yes, it's 1%. And is there a fixed number of trials? Yes, it's that 110,000. And good, Adam, that's exactly it. Y'all have got this. So that all I'm doing to find the expected value is just I'm taking that number of trials times my probability for success. This time a defect is a success, so that's weird. So y'all are doing great. I've got those 2 outcomes. So this is 1%. Remember that 1% is 1 over 100. Or if you're going to put it as a decimal, it's 0.01. I'm going to write it as a decimal just because yesterday when I was helping people with decimals, we were having trouble reading them. So I'm going to write that as a decimal. This is tenths place. So if I have a number in the tenths place, I read it as tenths. This is hundredths place. So when it's out here at the hundredths place, I read it as 1/100ths. And we know that because when we write it as a fraction, we write it as 1 over 100. So it's 1/100th. That's what it looks like as a decimal. We did that at the beginning of class, but I know that's been a long time ago. You could just multiply it that way, but I like to use my fractions because check this out. The zeros and the zeros go away. And so now I'm just multiplying 1 times that, which just gives me that 1,100. like Adam said. So I expect to have 1,100 defects each day. Now, what is the variance? So what's my variance going to be in this particular plan? How much is that going to vary? What's that variance going to be? So for the variance, all I do is I take that that mean, or my n times p there, and I multiply it times my q. So we have to figure out what is our probability for failure. If my probability for success is 1%, what's my probability for failure? So I have that 1,100 is my mean, and then my probability for failure is 99%, because 99% is the complement of 1%. Or I could write that as 1,100 times. As a decimal, it would look like this, 0.99. I would read that as 99 hundredths because it ends in the hundredths place. Or you could do it as times 99 over 100. Again, the 100, divide the top and bottom by 100. And then 99 times 11, well, 9. Add these two together to get 18. Carry 1, 9, 10. So my variance is 1,089. 99% is our probability for failure. It's a little bit weird because you don't think of defects as your probability for success, but you know, when I'm talking about what it is I'm looking for, so in this case my defects is my success, and then my failure would be this 99% of being okay. So it's weird, the terminology, but because we were looking for defects, then that's our success. So this is the variance for those defects. Now to find the standard deviation, I just take that and find the square root of it. So I'm just going to take that and find the square root of it to find the standard deviation. Look, this was 99 times 11. I'm going to go back to that 99 times 11, 11 times 99. I know that that multiplies to be this. And so then I know that 99, you can just use your calculator to find it. But I'm going to show you without a calculator how I would do this. This 11, notice that 99 breaks up to be 11 times 9. So here I have the square root of 11 times 11 times the square root of 9. Well, the square root of 11 times 11 is just 11. The square root of 9 is just 3. So I bet when you plugged that into your little calculator, you got 33 out. Okay, so my standard deviation is 33. So here's the question for you. 75% of the time, how many defects should I expect? Between what two numbers? How many defects should I expect? So I can draw out my number line to help me out. And remember, the way we find that, 75% of the time, at least 75% of the time, I'm looking at two standard deviations out. So I'm going to go start at my 1,100. That's on average. Good, y'all have got this. So you just add that 33 twice, and then subtract that 33 twice. Uh-oh, that part's hard. So you got 1,000, subtract 33, 70, 67. Is that what y'all got? And then subtract another 33 from that. so that you're at 34. So at least 75% of the time, I'm going to expect to get between 1,034 defects and 1,166 defects. So again, if more than 75% of the time I'm getting something out here, I'm getting big numbers, where I'm getting a lot, maybe I'm getting 1250 defects. That could happen once, it might happen once. But if it's happening over and over and over again, so that 75% of the time it's not between here, then I start looking at my machines and I start saying, where is there a mistake? Or is there one particular person on the line that's helping to make it make too many defects? Or what is it that's happening? Because that's not what I expect to happen. So that's exactly how we use that in statistics. We can find errors in things by looking for those outside that 75% or that 88.9%. So, all right, so there's an example. Let's do this one more example here. So we found our mean, we found our variance. Our variance was 1089, and then we found our standard deviation, and then we used Chevychev's to help us out. Let's do this one. And then I'm going to have a challenge for y'all today. All right, the doctor expects 1 out of every 5 patients they see to have high cholesterol. If the doctor sees 25 patients in a day, how many patients would be expected to have high cholesterol? So, if I want to know that expectation, or on average how many we have, Zoe, it depends on what the question's asking. So you have to really read to find out what it is that you want. Do you want the expectation? Do I want standard deviation? Do I want the variance? So you need to know the difference, and then you need to be able to answer the actual question that's there. So this is going to require you to actually, read and think about that question. So not every problem will have all 3 answers. It's going to depend on the question. Okay, so back here, is this a binomial? Can I use this formula? Or, just what makes sense? It's binomial to me. This expectation just makes sense. Good, Adam. It just totally makes sense that 1 out of every 5 patients they see have high cholesterol. Then how many do we expect to have high cholesterol? Well, it's just 1/5, 1 out of every 5 patients out of 25. So my expectation is just going to be the number of trials times probability. And yes, it is binomial because we have high cholesterol or we don't. Okay, so so it's have high cholesterol, don't. My probability remains the same of 1 out of 5. And then my fixed number of trials is 25. And Bo, that's exactly it. The setup there is 25 times that probability for success of 1 out of 5. And y'all have already found it for me. That mean, or my expectation, is that 5 of my patients have high cholesterol. What is the variance? Okay, so variance here, I'm going to take my mean, and I have to multiply it times my probability for failure. So in this case, what is the probability for failure here? So if 1/5 is my probability for success, then 4/5 is that probability for failure. So now I just multiply that. Well, this 5 and that 5 become 1, and I'm just left with the 4. So my variance is equal to 4. Now let's find the standard deviation. So the standard deviation, we just take the square root of that, and our standard deviation there is 2. So on average, we expect to, from the mean there, that distance from the mean, there's our standard deviation. Okay, so here's the question. I'll write it out so that you can kind of see what at least 75% of the time of the days the doctor should see between what two numbers of patients with high cholesterol. Cholesterol, can't spell that. That's kind of poorly worded, but it's kind of the idea. So at least 75% of the days, what's the range of patients we expect to see with high cholesterol? So notice I might just ask this question, but in order to answer this question, the first thing you have to do is find the mean, and then find the variance, and then find the standard deviation in order to be able to answer that question. But if I just ask you what is the expected value, or what is the mean, then you could just stop there. So in this question, my answer is just 5. For this question, I just do n times p, so I just get 5. So to answer your earlier question, Zoe, if I ask this question, my answer is 5 and I'm done. If I ask this question, I have to go through this whole process, plus now I have to do this and say, well, my mean is 5, so I'm adding that 2, I'm adding that 2, I'm subtracting the 2, I'm subtracting the 2, so at least 75% of the time, I'm going to get between 1 and 9 patients a day that have high cholesterol. So again, if I'm doing something where all of a sudden I'm getting a lot of patients every day, if I'm getting another one, a lot of patients every day, then I start wondering, what is it that moved into town that's given my constituency high cholesterol? Or what is our town doing different than some other town that is giving our town high cholesterol? Or maybe I want to do this. Maybe I want to lower the high cholesterol in my town. So I send out a campaign and I start telling people what to do to help lower their cholesterol. Exercise every day, stay away from red meat, don't eat carbohydrates, whatever to help you lower your cholesterol. So then I want to see, is my campaign working? Is this working? Have the people lowered their cholesterol? Then I could use this, and if all of a sudden, I'm getting something weird on the low end, then I can go, oh, it really is helping to, or maybe, it seems to be helping anyway. All right, Math Made Simple at Simpson Math. Thanks for watching.